file, and I will put them on the wiki page tomorrow to make sure that when everything is done, I can run a spell checker and maybe even find factors of 2 that I botched. So let us first start with a little warm-up exercise. The warm-up exercise is, yesterday we discussed resummation, and today I want to do resummation again. And in the intermediate step, we do it in such a way that it's nearly like a Parton shower, but analytical in the first step, okay? This goes under the name of resumming jet rates, and it's something that has been done in the 1990s. So people use, so the logic is to use a jet measure. It was called, at that time it was called the Durham jet measure, and so I couldn't refrain from putting it. It's actually KT jets. And now because we do E plus E minus colliders, which are much easier to handle in a way, instead of transverse momenta, we take the energies and we directly calculate the angle between 2 particles. And so just to remind you, the logic is that you cluster, you look at your partons and you cluster them backwards. So you check for the pair with the smallest distance, and you make 1 parton out of 2 until the smallest distance is larger than Q jet, some scale. And then you stop and you say, well, now I have n jets, the n remaining partons. And what you can do now is you can use Pseudo form factor and its probabilistic interpretation to calculate jet rates. So we are not discussing cross sections, we are discussing rates, probabilities. And that works fairly well because the Pseudo form factors, as we discussed yesterday very briefly, are probabilities for no emission. Okay? So let's take a look let's take a look. So the no emission probability is Pseudo form factor for quark or gluon, and it's no emission between 2 scales, upper scale, lower scale, and it's exponential integral over transverse momentum, color factor alpha s over 2 pi, and the same form a log plus b. Pretty much identical to what we had yesterday. Now, this is the probability for not having an emission. Okay. Now, let us assume we want to calculate a 2-jet rate. It's the simplest thing in E plus E minus going to hadrons because the underlying diagram is E plus E minus going to QQ bar. And the 2 quarks will typically be back to back. So naively you have 2 jets, unless you have 3 jets or 4. But you will typically have at least 2 jets, okay? So for having 2 jets, you are not allowed to have a third one, right? If you want to have 2 and exactly 2 jets. Having a third jet would be really bad because then you don't have 2 anymore. So based on this, if I would ask you to write down an expression for what is the 2-jet rate, would you be able to do that? The 2-jet rate is the probability that is given by the probability that neither the quark nor the anti-quark emit a gluon at a scale above the jet scale, right? Because would they emit a gluon above the jet scale, the gluon would be a third jet. Can you now write down what it looks like? Any ideas? Or yes, no, maybe? Maybe.
If you have 2 jets and neither of them should emit another jet, you square that probability?
Exactly. And you would have center of mass energy or whatever, upper scale, and jet scale here, right? Well done. So this is exactly what it is. You have to go over here, click and, oops. Okay, so the two-jet rate, just be, as you said, the squared thing. Now, let us see whether we can do a three-jet rate. Same logic, to have three jets, what must happen is the following. One of the two quarks is not allowed to emit, right? And you have two options because either the quark or the anti-quark will emit and the other one will not emit, therefore you have a factor of 2. Then you must have an emission somewhere between Q-jet and center of mass energy, so I should have put limits here. So it's Q-jet to center of mass energy. You must have an emission. Then the quark that emitted should not have emitted before, because otherwise you would have a harder jet, right? And you would have 4. And the two outgoing guys are also not allowed to emit anything above the jet scale, because then again you would have 4. So what you basically do is you use the Pseudo form factor as a measure to suppress radiation. And the trick is, we know, we already know in this funny language how stuff gets emitted. Because what we have in the Pseudo form factor, here, this stuff here, this bit here is the emission term, you remember? We exponentiate the emission term, put a minus in front of it for the compensation, so we know what the emissions look like. We have a color factor, alpha s over 2 pi, and then these terms a and b. Yeah? So we could iterate, and we could do 4 jet rates, 5 jet rates, etc. So we would draw like Feynman diagrams, and what you do is, practically speaking, for every line you put a Pseudo form factor, and for every vertex you put one of these terms. And that actually works remarkably well. Not perfect, but remarkably well. So in a way, this is what we would put in a parton shower if we wanted to simulate now. We could put exactly these guys into parton shower. Start with 2 quarks, use the Pseudo form factor. Because it's a probability, we just take a random number, we compare a random number with Pseudo form factor, we solve for the next scale, and so on and so forth. I come back to that, but this is, in a way, this is like the link between what we did before, summation, and what I'm going to show you now, the parton shower. They're deeply related. Okay. Ready till now? Yeah? Questions? Yes, no, maybe? No? Okay. So let us see what the parton shower does. And we start from a completely different angle. We do a little bit of high school physics. It's nice to know that in high school physics we do really posh stuff, but we don't call it posh names. So I'm fairly certain you've seen in high school physics the radioactive decay law. So you have a radioactive isotope or a bunch of radioactive isotopes, and you ask yourself, how many isotopes are left after a certain time? And so what you do is you define a non-decay probability, and then it's exponential of minus t over tau, and I forget about factors of log 2 or so because I can't be bothered really. But that is pretty much what it looks like. The probability for an isotope to decay at a time, well, magic trick number 1, we call it unitarity, but it's a trivial thing. The probability of something to decay is the probability of 1 minus it not to decay. Because it either decays or not. So that's unitarity, right? It either decays or not. We call it unitarity, others call it common sense, but okay. it's a little, when we push it a little bit, it becomes more complicated, but ultimately this is what unitarity means. It either happens or not. Okay, so because it either happens or not, we know that the decay probability is 1 minus the no decay probability, because they have to add up to 1. So the probability for an isotope to decay at any time t is the derivative, and what you get is 1 over tau, which is the half-life, like the inverse matrix element for decay. And you get this exponential of minus t over tau. Why do you get this? You get it because for the isotope to decay at time t, it cannot have decayed before. And you have to count for that. Okay? So you realize that this thing that you learned in high school is a pseudo-conform factor, yeah? So you did pseudo-conform factors in high school. People just cheated you of the fun to know the right name. But I'm fairly certain it gives you a warm feeling now. Now, let us make life a little bit more complicated. In a fantasy world, let us say our half-life, 1 over tau, gamma, isn't constant, so it depends on time. So instead of doing gamma t, you have to integrate over time, because this gamma may change with time for whatever bizarre reason. So we do the same thing now. The decay probability at any given time now is 1 over tau, which is my gamma of t, times a pseudo-conform factor, where I have a notion of time in it now. So instead of doing gamma t, I'll do integral gamma dt. And this is pretty much how Parton showers work. So we produce something that tells us a parton decays, and we do an ordering. But instead of an ordering in time, we do an ordering in scale. Pretty much what we did before in this analytical thing. I just arrive at it now from a different angle. So we order our emissions in scale playing the role of time, and then we can repeat exactly the same game. Okay, now let us assume we have absolutely no idea about resummation and what we did before. Just, I want to show you that with the same logic you arrive at the same, with different logic you arrive at the same thing. So let us go back and look at the Altarelli-Parisi equation. You remember that the Altarelli-Parisi equation describes the scaling behavior of the parton distribution function. And what it basically does is it says the change in a parton distribution function at a scale is driven by the, I do it in a very simplified way, by the parton distribution function you have before times something that lets the parton split. So it's the same thing. You ask yourself, where is the parton? And it either split it or not. And so the change must be driven by that it split it, because if it hadn't split, it couldn't change. And we know what drives the change. The change is the splitting function. So it seems kind of logical that we use the splitting function as a kernel for our pseudo-conform factor. And you see, instead of just doing this integrated a and b that I had before, a log kt squared plus b, I now get a notion of that the splitting function depends on the energy splitting. So I'm becoming a little bit more differential. So I have a change in scale, but the driver now is not independent of the splitting kinematics, because the splitting function does not only depend on q squared implicitly, but it also depends on how the energy is distributed after the splitting. Okay, so how can we arrive at the splitting function? I told you I want to calculate it, and I want to give you an idea how to calculate it. So let us start with the simplest process in QCD that involves the splitting. We do E plus E minus going to 3 partons or 3 jets. So we ask ourselves, what is the matrix element for the production of a QQ bar gluon final state? And I guess this is one of the things that you may calculate in quantum field theory classes, this x1 squared plus x2 squared. Who of you did calculate it in school? No one. You're joking. Really? Okay. Do you have an idea how you would calculate it? Feynman diagram, trace, polarization, vada, yeah? Okay, let's assume we all calculate it, because in principle we know it, and you're a little bit platonic, right? You don't get dirty. I accept that. It's the old people who get dirty. So anyway, let us assume you calculated this. This is something you will probably find in every book on QCD ever written by man. And what you see here is the following. So, sir? That's true, yeah. Ever written by people. Ah. Yeah, I was told recently that I'm not allowed to use the word manpower anymore. It's people power. I can really bend my head around it, but it's too complicated for me. I have to relearn English. Okay. So x1 and x2 are the energy fractions the quarks have after the splitting. So before the splitting, x1 and x2 are 1. And after the splitting, it's less. And what you see is, if x1 and x2 go to 1, this thing will explode. Now, we discussed before soft and collinear divergences, and the divergence structures, the way I presented them beforehand, were dependent on energy and transverse momentum. And in this form, you don't see energy and transverse momentum of the gluon anymore, because I express everything with quarks, so that is not really nice. What I do now is, instead of using the energies of the quarks after the splitting, I want to go back and say, I want to use the gluon energy, and I want to use the opening angle with respect to the quark. What I get now is the following. I get the same CF alpha S over pi, then I get a slightly different expression. And when you look at it, you see again, we have a soft divergence, which is when x3 goes to 0, and we have a collinear divergence when the angle with respect to the quark is either 0 or pi. Where does the pi angle come from? Where does this divergence come from? Any idea? It's exactly, yeah, it's the other quark. Well done. So I used the quark, but if I would have used the anti-quark, it's, you know, the opposite direction. Well done. Okay. So I see the same thing, and remarkably, this full thing as before is proportional to the cross-section for producing the quark-anti-quark in the first place. So this thing here is something that you could call like a splitting kernel. You start with quark, anti-quark, and then you split it. So let us massage it a little bit further. So having the quark and the anti-quark lumped together is slightly annoying. So what I do is I write sine squared as 1 minus cos times 1 plus cos, and I take it apart. And then I realize that the quark goes in the direction opposite to the anti-quark. So if I replace the quark here with the anti-quark, I have to flip the sign. Yeah, now I can write it in whatever way I want to. So, but this is proportional to a transverse momentum with respect to the quark, and this is proportional to the transverse momentum with respect to the anti-quark. So I have decomposed my radiation pattern into 2 parts. One part with respect to the quark and the other part with respect to the anti-quark. And then I can write it as CF alpha S over 2 pi, d theta squared over theta squared splitting function. Now, do we know what the splitting function looks like? Yeah, sure as hell we do. We just look into this thing here. And what you realize is, if X3 is the energy of the gluon after the splitting, the energy of the quark after the splitting would be 1 minus X3 if you factorize it and you pretend the other quark doesn't feel the pain. So if we replace X3 by 1 minus Z, you get 1 plus Z squared divided by 1 minus Z. That's exactly the splitting function. And you get some finite term that is not logarithmic, so this is where the two guys, where the quark and the anti-quark still communicate. And we come back to that term in about 10 minutes, yeah? But if you look only for the logarithmic parts, this is the logarithmic part and this is some finite part. All the logarithms sit here. Okay? So this is how you see what the splitting function looks like, yeah? I don't think so. I don't think so. Because I still integrate from 0 to pi. Yeah, so you kind of you also change the definition of the angle, so it compensates. Well spotted. It's a good question. Short moment of thinking. Good. Okay. Yeah, not so important. The only thing I want to point out is the following. In order to capture this collinear divergence, it doesn't matter whether you go angle, transverse momentum, or mass. They have the same behavior, but they introduce slightly different finite terms, and that means that different ordering parameters are better than others, and we see that maybe later. Okay. So we know how to write this up. Now again, when we did the analytic resummation, or in all our analytical stuff, we always said, oh yeah, but we have to do something. There's a divergence. We have to kind of cut it. I want to come back to that because it's an important question, and we can now formulate it again with pseudo-conform factors in a kind of a nice way. So when you ask yourself what is a parton, you practically speaking ask the question, what kind of emissions do we want to capture and which kind of emissions do we not want to capture? And it's clear, if the parton has enough energy and a big enough angle, it will be resolved because it will have the potential to make extra hadrons, like extra pions, extra protons, whatever. If on the other hand, the gluon is emitted too collinearly or too soft, it will most likely recombine with the original quark and end up in the same hadron. And we discussed this, I think, on Monday, that this kind of gives us a lower limit for which K-perp we put in. Yeah? That we regularize this by demanding that the emitted gluon has a minimal transverse momentum with respect to the quark. Now, the only point I want to make is if we do that, in the Sudakov picture, it's a discussion that I think Vito had yesterday. You have one part that is resolved, and you have another part that is unresolved, which is a combination, pictorially speaking, of unresolved, very soft, very collinear real plus the virtuals. And in terms of probabilities, it has to add up to 1. It's exactly the same argument as yesterday. So either resolve it or you do not resolve it, and the probabilities have to add up to 1. So if I know how to calculate this, I know how to calculate this and vice versa. Or in other words, by going from matrix elements and cross-sections to probabilities, I implicitly use the Kinoshita-Lee-Naumburg theorem that tells me that stuff cancels. It's the same argument that we had yesterday. You can either calculate this with an upper cutoff, or you can calculate this with a lower cutoff, and that gives you the same term in the exponential because we do it in probabilities, and we forget about some non-leading terms. So in a certain approximation, logarithmic approximation, you can directly exponentiate, and that makes life so much easier. Yeah.
Question, I guess, practically about that. With the last term, there's some logarithmic divergence in KT. How does that translate into the self-energy correction?
In here you have 1 over epsilon poles.
Oh, okay. So you're doing it with. Okay.
You combine them because you know this thing here. If you put a KT cut, is infrared finite. This thing here per se is not infrared finite. You have to combine it with this to have infrared finite. That's why I add them. Okay. Because otherwise I would have to convince you that I can exponentiate infinity, which is probably not the optimal solution. Yeah. Okay. So I write this to get rid of the 1 over epsilon squared and 1 over epsilon terms. Yep.
Just along this line, I understand that the probability of resolved downrow should add up to 1. But I think this should only be the argument to all orders. But we previously did for each fixed order, we add up to 1. Is that always true, or is that still true?
Yes, also for fixed order. If you the very moment you use the word probability, it adds up to 1.
At each order.
At each order, because look, if the probability for you emitting a photon now or not is whatever, but I know that if I add the probability of you not emitting something, then it's 1 because you either emit or you don't. And this is true for every single emission. Now the catch is what the exponentiation allows you is to take into account the probabilities to all orders. Because you use the word probability, you implicitly are already at all orders. Yeah? Because you do not calculate a matrix element anymore, you calculate a probability. It's slightly different. Yeah? Okay. Now, yeah, okay. So, same game again. Differential probability comes with the splitting function, and the splitting function integrate over Z gives us this gamma. How do I see this? I see it by saying, okay, not so good. What I want to do is I want to integrate this thing with, let me just call it an epsilon and a 1 minus epsilon here. And this epsilon I can put to 0 ultimately, because it will not give me a log. So if I integrate this, if I want to integrate this, I can write the same thing as dz 2 over 1 minus z minus 1 plus z, yeah? You see that. 1 minus z times 1 plus z gives me 1 minus z squared. I put it here. The 2 minus 1 minus z squared is 1 plus z squared. Now if I integrate this term isn't divergent, so I could, and if epsilon is sufficiently small, I can just say this thing is integrated from 0 to 1. Yeah? So this gives me 3/2. And this thing here will give me something that looks like 2 logarithm of epsilon. And then I have terms of order epsilon that I ignore. Okay? And this is how the integral of the splitting functions gives you the terms a and b. You remember the two? You remember the two and the 3? Yeah? That's how it comes. Okay, so we know how to deal with one emission. The only thing I want to say now is if you have many emissions, we order them. What I said before was we order them because scale plays the role of time, but if you do this ordering in scale, you can convince yourself that, so what happens, that this is how you get the maximal logs, because if you use q1 squared as the upper limit of q2 squared, you get something that looks like log q1 squared, but you integrate over q1 squared. And that's how you get the maximal number of logs by ordering. If you break the ordering, you start dropping logarithms. Yeah? It is because when you let us go back to this. So the trick is the following: you do this d cube herb squared, and this cube herb squared here enters as a log. So if you integrate over d cube herb squared over cube herb squared, this is d log cube herb squared times log cube herb squared. If you would not take the upper limit from this emission, but say q squared again, you wouldn't get logs in. You wouldn't get the logs iterated. So you would start dropping logs. That's why in parton showers and typically in all resummations you have an ordering in some you have an ordering in the parameter that generates you the logs. Yeah. So if you want to do a resummation of transverse momenta, you have to order your logarithms in transverse momenta and put them into each other like a Russian doll. If you wanted to do something like soft gluon resummation a la BFKL, you would have to order in soft gluon energies because you want to have the logarithms in the energies. Here we want to have the logarithms in transverse momenta. That's why we order in transverse momenta, and this gives you the maximal logs. Okay. So we continue a little bit with our anatomy of the parton showers. We have alpha s. What is the right scale to take for alpha s? I claimed k perp squared is the right scale for alpha s. No one ever challenged me. But I mean, it's just a randomization scale. I should be allowed to take whatever I want. What is true, however, is the following. When you think of higher orders, you start seeing that there's terms like vacuum polarizations or vertex corrections. And by using specific choices, you can show that the choice of k perp resums these vacuum bubbles and the rainbow diagrams in the vertex corrections. Yeah? So this is quite complicated to see, so I just claim it and you have to look it up in literature. But it's something that is well known already from QED. If you do the right choice, you implicitly, because you have the beta function that is driven by these bubbles, and because of the randomization conditions, self energies and vertex corrections talk to each other, by doing a smart choice, you insert the right beta zero into your equation, and this right beta zero actually has to do with the fact that you have these diagrams. This is the logic of why a scale choice can help you to resum certain virtual corrections. Okay, so this k perp naively sounds good because k perp is the scale at which the splitting happens. This is how we describe it. But the deeper reason is that in fact virtual corrections are being taken into account by this choice, which is really neat. It's always nice to see your prejudice is confirmed. Makes you horribly biased. Okay. Now, let us discuss something that is a little bit more subtle. I go back to QED because in QCD it's more complicated. Let us start with QED. It's the same logic that we applied before. We do the following. We have a virtual photon. We produce an E plus E minus pair, and we ask ourselves, how can we produce a secondary photon? And you can argue in many different ways. I just give you the gist of it. The gist is the following. If the wavelength of the photon, the transverse wavelength, is larger than the transverse distance of the plus and minus pair, it will not see two independent charges, right? It's like microscope. If the wavelength of your microscope is larger than the object you want to look at, you don't see the inner structure of the object you look at. What you would see is a dipole. What happens when you have a dipole instead of a monopole? What happens to the potential? What happens to the fields? Come on, electrodynamics.
Drops off as an extra factor of 1 over r.
So instead of 1 over r for the potential, you have something that is worse. So in other words, the dipole field, the probability, the chance of a dipole to emit is weaker than of a monopole. You could still have the dipole, but we're not interested in subleading stuff here. We want to see the big locks, right? So in other words, the transverse wavelength of this thing must be smaller than the transverse distance of the thing. Otherwise, we can't see it. And now we can go back to all these wonderful arguments of, oh, we have an energy disbalance. How long does it take for the photon to be formed? And how far do the E plus E minus pair separate during that time? And if you put it all together, you start realizing that the opening angle of the photon with respect to its emitter has to be smaller than the opening angle of the plus E minus pair. In other words, if the opening angle of the photon is bigger than the plus E minus pair, it only sees the dipole. It doesn't see two monopoles. So is this relevant? So pictorially speaking, now let us go to the case of QCD. Let us say we have a quark emitting a gluon, and we ask these guys to emit another gluon. What it means is the following. If the opening angle of the soft gluon in red is larger than the opening angle of the quark and the gluon, it doesn't see the quark and the gluon individually, it only sees the combined color charge. It's the same logic, right? So that means the large angle stuff has to happen before the small angle stuff happens, because otherwise the large angle stuff couldn't see the components of the small angle stuff. Can't see it, right? Why is this relevant? Sounds a little bit technical, but I have a beautiful plot from the 9th. I think Michelangelo knows this plot better than I do. So I think it's one of the nicest QCD plots, the most compelling QCD plots I've seen, that describes something very subtle. Now, let me unwind a step before we go into that plot. What I just claimed is the following. I said that there is a quantum effect, quantum coherence. Can we resolve individual partons or not in subsequent emissions? And I could have calculated explicitly, and I could have convinced myself that there's destructive interference between the two individual emissions if the wavelength is too big. You could do it analytically, but it's boring. This puts a constraint on single emissions. So I can ask myself, is there a way of how I get non-trivial quantum corrections that come in second emissions? Can I absorb them in my description of single emissions? With the choice of K-perp, I take care of virtual corrections. With the choice of the ordering parameter, I take care of quantum effects in subsequent emissions in such a way that I can still describe it in a single emission language. Okay? And now we look at this plot and we ask ourselves, are these quantum effects visible? Are they important? So the measurement is the following. It's Tevatron, but you could do the same measurement at the LHC. You have two jets where the hardest jet is relatively hard, 110 GeV transverse energy, And then you have a third jet, which is probably softer because we order them in energy. And we now look for stuff like, for instance, the distance in phase space between the second and the third jet. Or we look for the rapidity distribution of the third jet. Now what is clear is the following. The opening angle between those two guys has to be smaller not only than the opening angle between these guys, but you also have to take into account that at the tevatron you have incoming color charges. So by, for instance, making a quark pair, if you have quark anti-quark annihilation and production, you have two two color charges that go through the diagram at an angle. And these angles are actually the relevant ones because you follow the color flow in your angles. So in other words, the opening angle of an extra gluon emitted by this guy has to be smaller than the opening angle of this quark with respect to the incoming beam. Right? Incoming beam deflects it, so you have an opening angle, and if you want to emit, the opening angle of the extra gluon has to be smaller than the opening angle of the quark. Okay, so you see 4 Monte Carlos, Herwig that does angular ordering, Pythia that doesn't do angular ordering, Pythia hacked, which now does angular ordering. EtherJet and Pythia had roughly the same parton shower, but while Torbjörn hacked his stuff, EtherJet didn't care. Really, they never did it. And you see the effect is clearly visible. It's more pronounced when you look at the pseudo rapidity of the third jet. The third jet in its pseudo rapidity wants to follow the pseudo rapidities of the 2 leading jets. That's why you see this camel-like structure. If you don't let it follow, then the third jet can be wherever it wants to. In particular, it can be far away from the 2 leading jets, and that's why you don't have a camel but a dromedar. Okay? So angular ordering is the difference between a camel and a dromedar. But it matters. If you look for new physics and your signal depends on where the jets are, you better get the jets right. Sounds kind of logical, I guess. So, yeah. If you would not have understood it, this would have looked like new physics, the decay of a heavy resonance into jets. Beautiful essential, clearly must be a heavy resonance. Okay, so that's angular ordering. They are from Michelangelo knows it better, 91, 92? 94. Pythia is this now. And actually they completely changed their shower. This shower was ordered in virtual mass and had an explicit angular veto as an afterburner. And by now, practically all parton showers order in something that is transverse momentum or energy scaled angle. And these parton showers passed this test actually quite well. Yeah? No, it's one of the beautiful things about Pythia. Torbjörn was absolutely fantastic in looking at data, and continues to be absolutely fantastic actually, by looking at data, realizing what goes wrong and adjusting his code. He's absolutely superb in boiling it down to the essential and adding the right piece of physics into it. Fantastic intuition, so it's quite impressive. And he did this now for 30 odd years, so you cannot be but impressed. Okay. So just summary for this all order stuff, because it was kind of stretched over 3 lectures. We briefly discussed that there's different resumation techniques for different situations. So you basically identify, it has to do with what phase space you fill or you don't fill. You try to identify a parameter that kind of tells you how you fill the phase space. You use this parameter as an ordering parameter in a pseudo-conform factor, and that allows you to, or pseudo-conf-like factor, like an exponential, and that allows you to resum logs. So the common denominator, as I said, is how you fill the soft and collinear phase space, and you can have slightly different logic depending on the kinematical situation you're in. What happens effectively is this means you have to replace alpha s with something that is alpha s times the logarithm, where the logarithm encapsulates the phase space constraint. And all these logarithms and all the kind of resummation that you want to do is incorporated in something called a pseudo-conform factor. In some cases, you get a factor that looks very similar, but it's not a pseudo-conform factor, and then it's called a non-pseudo-conform factor. But it formally looks like a pseudo-conform factor, so it just has a slightly different interpretation. And it allows us to go into Monte Carlo, because once you have it probabilistic, you can always compare with random numbers. That is the beauty. Now, I want to use the last 20 minutes or so to show you a little bit of how you push the precision. So we are now at a stage of simulation of about 95. We're about at 95. Okay, so we now try to make a jump of at least 10, maybe even 20 years. So let's try first to go past 95. And I go back to plus or minus, and I'll try to explain with a simple example what the name of the game here is. You remember when I derived the splitting function, that there was this extra term that didn't have a sine squared theta, that I said, oh, this is a finite term. This is a reminder that it's two quarks that are kind of involved, and it's not logarithmic, so we forget about it. Now, we can ask ourselves, how big is this term? And it turns, so basically the question I ask is, what is the difference between taking the two diagrams and adding them before squaring them? Or this is what you would do in the full calculation, or what happens, or what is the difference of this with respect to the parton shower, where I take the diagrams in a certain limit and square them before adding. So what is the difference between coherent and incoherent sum? And we can plot it. Sometimes it's really nice to plot it. So in this x1, x2 space that we had before, I can plot the ratio of this over this. And you see that the ratio is 1 when either x1 or x2 or both go to 1. So in the limit where the logs are big, where the matrix element starts to diverge, the approximation of forgetting about the interference term is really good. But when I go away from this limit, I start realizing that the interference term can be large and can be of the order of a factor of 2. Now, these are not necessarily events that happen very often, for a very simple reason. There's no big logarithm that would drive the emission. It's finite terms. But if you want to get this region right, you would have to live with the fact that the parton shower will overestimate it by about a factor of 2. So there's an implicit danger that the parton shower, in that specific case, overestimates the jet production. Yeah? And the harder the third jet, the worse the parton shower. And that's not nice. So there's a simple trick we can do. The simple trick goes as follows. We calculate the real emission matrix element, and we calculate the thing, what the parton shower would do. Born times whatever splitting kernel we have. And this is pretty much the plot I did here. I did R over B times K. And what you can do now is you say you let your parton shower run, and you say for say the first emission, you form this ratio, and you know it's a number between 0 or 1. And then you compare with a random number, and you accept or reject this emission. So in other words, you reweight your parton shower such that it reproduces the matrix element. See what I mean? I'm going to formalize it a little bit later, but this works only because R is smaller than B times K all over phase space. And at about 1995, Herwig and Pythia authors realized that for typical processes like quarks going to gauge boson or gauge boson going to quarks, or top decay into BW, this holds true. The real emission matrix element is always smaller than Born times kernel if you do it right. If you do it right, it's a statement because there's something here that you wouldn't get really in the parton shower. The parton shower would start at the mass of the gauge boson, and that means you cannot produce jets that are harder than the gauge boson. And so here you have to think about how you fill this phase space. But in principle, once you forget about this, the real emission matrix element will always be smaller than Born times kernel, Born times splitting kernel. So you can do the reweighting. Sure. In this process, yes. This is not generally true. Exactly. Exactly, yeah. Yeah. There's other processes where, you know, it's a quantum interference. It can go either way. And if you're lucky, it goes the interference is negative, and then you can do the reweighting. If it's positive, you can try to produce an overestimator for the matrix element and multiply stuff out. Yeah, it's only bad if your overestimator goes to infinity. Yeah. And the reason why it's exactly, it's the fermion, and you either go with or against the fermion flow, and that gives you a sign. Well spotted. Okay, so let us look what the first emission looks like. Now, I kind of push you now into a place where I'm perfectly happy if you interrupt me at any time and say, wait a second, we didn't get it, because this is, I try to formalize in a way that is maybe tough. So I try to calculate a cross-section, and I start with the Born configuration. And this can contain PDFs or not. It's just a sketch. If it contains PDFs, life is a little bit more complicated, but formally it's the same. Now, I have to, for the first emission, I have two options. Either it happens or it doesn't happen. If the emission doesn't happen, I take a pseudo-conform factor between whatever scale my Born configuration gives me as a parton shower starting scale and the cutoff of the parton shower. Yeah? So this thing here looks like a pseudo-conform factor, but instead of a splitting kernel, I now take real over Born. I could have taken a parton shower splitting kernel, but I take a real over Born because I want to show you what I do with the matrix element correction. If it was just the parton shower, I wouldn't have R over B, but I would have splitting functions here. And I would call them K, like splitting kernel. Okay. But then, so this is the non-emission, but now we want to have the emission. And the emission is given by the matrix element for the emission, and you see how the Born would cancel. Yeah? So here you get the exact matrix element, but now you have to make sure that you haven't emitted before. Same logic as before. What I did, however, was I effectively replaced the splitting kernel with R over B. So I go back because this is kind of a fun thing to do. It's a little bit like what I did here. I have my 3-jet rate, and I now scale it with the production of my inclusive sample. I take my so in my 3-jet rate I have an emission term, and this emission term sits also in my Pseudo-Curve form factor that I haven't emitted before. Yeah? So, I do exactly the same here. I do exactly the same here. I take my emission term, but now I write my emission term in such a way that I reproduce the exact right matrix element. And I could have done this in the equation before by, instead of taking the gamma, to do x1 squared plus x2 squared divided by 1 minus x1, 1 minus x2. This is what I've practically speaking just did to you. Now, what happens here also, and now we come back to unitarity, this thing here is a 1. Yeah, this is a 1 because either something is emitted or not. Now, if you start calculating, you start realizing for that to be exactly 1, the argument in the Pseudo-Curve has to be exactly the argument of the splitting term, because only then you have like a complete integral. Or in other words, this is the negative derivative with respect to that. Okay. So what I achieved with this is the following. I achieved, so in my language of alphas and logs, I know that for every emission I have 2 logarithms. My Parton-Shaw to some degree gets 1, maybe 2 logarithms right. Judgment is out. So the Parton-Shower in terms of emission pattern gets the green terms right, more or less. So if your Parton-Shower is really good, then it will probably get, for simple processes, will get 2 logs right. And by doing this reweighting, I get the first non-logarithmic term correct in the emission pattern. I don't get it correct for the overall rate. My overall rate, my overall cross-section is still Born because I just multiplied Born with 1. So this is a Born cross-section, but the pattern of the first emission is exact to order alpha. So if I would multiply this thing with my k factor, I would have a simulation that is next to leading order accurate. First emission right, total rate right. Okay.
So question.
Yep.
In what cases do you want to apply this? I mean, if you have like the real emission amplitude radius, so why not you do it the correction at total next to leading order and only leading order with Parton?
Sorry, you are, let me try whether I understand the question because I'm not quite sure I understood it right. So you basically ask, why do I use the Parton-Shaw when I have the reals?
Yes, I guess. The question was, yeah, more or less, if I have the reals, why don't I take reals and do the Parton-Shawing then? So kind of next to leading order and then Parton-Shawing? Or why don't I use, yeah, why do I want to use leading order and then Parton-Shawing with like real correction?
So I let me give you a simple explanation and a complicated explanation. The simple explanation is the following. This is something that you can do inside your parton shower with a very simple reweighting. So it comes for completely free. You don't even have to work hard. That's why people implement very early. If you want to have the next to leading order rate as well, in that case, you just calculate inclusively and you multiply. And that's perfectly fine. But you would do this afterwards. And in fact, for experimenters, quite often, it doesn't really matter what the overall rate is because they adjust the overall rate to their measurement. Yeah? Exactly, it's just a normalization. So at that level, the next leading order correction is just a normalization factor. The not so simple answer is if you wait 2 more minutes, I show you how to get it the next leading order included as well, which is it's nice, but you will see that the simplest way to getting the next leading order in is pretty much just matrix element reweighting and getting the factor in the calculation right. Okay. Okay, here we go, next leading order. So we now want to turn this blue point rate into, we get it completely right, in, not only the shape of the first emission, but also the total rate of the full process. So, so we are now, when it comes to next leading order matching, at about 2005. Okay, so we made a jump of 10. We make a jump of 10 years now. I explain it with POHEC because POHEC is pretty much just matrix element correction. And I will then explain MC at NLO. Historically, MC at NLO came before POHEC. But pedagogically, I like the reverse order better. So the first thing, and we already discussed this, is we replace the splitting kernels with R over B. And this gives us our pseudo-conform factor. And what POHEC did was they realized that they can do this for every process, not only for the 1 or 2 processes where R over B is smaller than 1. They just do it for every process. Irrespective of whether the interference is positive or negative, you can always do that. That is the first trick you have to keep in mind. R over B will always be a positive number because R is the leading order matrix element squared, it's positive, and B is the leading order matrix element squared, which is positive. So this is always a positive number, and that means this exponential is always smaller than 1. And this has nothing to do with the sign of the interference. So that was kind of neat. The other thing you can do is, you can say, well, actually, I would love to have a Born cross-section. Sorry, I would love to have a Born kinematics, but I want to have it in such a way that when I integrate over Born, I get the next leading order result. So how do you do that? You do that by saying, well, I take the Born, I add my virtual, I add my subtraction. And then I fix the Born kinematics and calculate real minus subtraction for Born kinematics times an extra emission. You see where this is going, yeah? So you basically integrate out the extra emission, and that means you get Born kinematics with next leading order differential cross-section. Okay. And we're already there because you take this Born, you use exactly the same Sudakov logic as before, and the only thing you have to do now is you have to convince yourself that all the terms that come from the interplay between Sudakov and whatever is in this modified Born, that these terms are 1 order higher. And then you say, well, I never said we are next to leading order accurate, we're only next to leading order accurate. And if there's extra terms alpha s squared, beyond our accuracy. So let us do that. So this is the Pohek. This is the Pohek thing. As before, Born emission, no emission or emission, with the difference now that the Born is weighted in such a way that when you integrate over phase space, you get the full next leading order result. So you get something. You practically put some local k factor, kinematics dependent local k factor onto the Born with what I did before. And what you have to do now is the following. You have to try to go to order alpha s and see that you don't get anything that you don't want to get. And the first thing, and this is in particular true for the emission pattern, but now you know that R over B is already of order alpha s. Yes? Because it's one emission. So every term in this Born that is in this modified Born that is not Born comes with an extra order alpha s. So I cancelled the Born part in here with this, and this is order alpha s, and all the higher order terms that are in here, if I combine them with whatever I have here, are one order higher. And the same, of course, is true when I expand the pseudo-conform factor. Okay? So the only terms I generate that I don't control are order alpha s squared. Okay. Now there's a little bit of a problem. In the original Pohek, there is something that is tricky, and I will tell you what it is, and it will explain why MCAT NLO works. So what you do here is the following. Whatever your kinematic configuration is, you map it onto some underlying Born, and you apply a local k factor. Now, let us think about the case of, say, gluon fusion into Higgs. Gluon fusion into Higgs has a k factor, an NLO k factor, that is larger than 2. Gluon fusion into Higgs plus a jet has a k factor that is only of the order of 1.4, 1.5. Now, if you have a configuration like Higgs plus jet, Pohek implicitly clusters it back to glu to Higgs, so Higgs without a jet, and attaches a k factor that is not correct. And the Higgs boson looks interesting. Let us compare it with the next to leading order. So this is the next to leading order. And it now comes with a k factor that is relatively large, and that is entirely driven by the fact that you apply a k factor of 2.2 to something that doesn't have a k factor in next to leading order. Because at next to leading order, the inbuilt accuracy of Pohek doesn't even have a k factor on the glu Higgs to gluon, because it's only leading order. So if the k factors were independent of emissions, this would work really well, but they aren't. And in fact, I come back to that, the more QCD particles in the final state you have, empirically, the smaller the k factor. Yep. So the logic is the following. You divide the phase space into two parts. You divide it into a part that you call soft, and you say, well, if it's soft, then it isn't an extra jet or so. And I can then apply my k factor as before. And if it's hard, I don't apply a k factor. So you split your real into, and the real is the driver of the big k factor here, in fact. You split your real into two parts, soft and hard. The soft gets attached with the k factor, the hard doesn't get the k factor. So in your modified Born, you now integrate only over the soft part of the real. And for the pseudo-conf, you only take the soft part, and then you add in by hand the hard part without any k factor. Now, in POHEC, this is done by using a profile function that so naively you could take a theta function. But that's ugly because then you see a step. So we don't like steps. We like to smooth it out. So you take a profile function. This is the profile function they took. And h becomes a tunable parameter. Now, what do you think when you tune h? What value will h roughly get? Any idea? I give you a hint. When you do a when you write down your cross section, you use a factorization scale, and the factorization scale says anything up to the scale is in the PDFs, and we resum it and modify it, and everything that is above we make explicit. What factorization scale would you take for glue to Higgs? Higgs mass, right? Because it's the only mass in the system. What h would you take if you were completely naive? Higgs mass. What comes out of the tuning? Higgs mass within 10%. Okay? So in other words, by applying a big K factor at scales above the natural scale of the Higgs, you kind of make a mistake. And if you were really vicious, you would say you start breaking factorization theorems. So this kind of decomposition reinstates the dignity of factorization. And that's kind of beautiful. Hmm? And now we can do the same, and this is pretty much my last slide for today. You can do the same thing with MC at NLO. Now in MC at NLO you also do soft versus hard, but instead of doing it with a scale, you say, we actually know what soft physics is, the soft collinear bit. It's done by the parton shower. So instead of taking a profile function, say, we take in our modified Born, we take exactly the splitting kernels, which actually are also the subtraction terms. So you take your modified Born, and because the soft bit is exactly the bit that you would have subtracted out of your real emission anyway. And then you can say, okay, my Sudakov is the original Sudakov with the original splitting kernel, and I generate my emissions with the original splitting kernel, but the error I make is now the full real minus this thing here. And that is what I add by hand. And this kind of makes sure that, well, you take whatever scale you think your parton shower would take. So you use the parton shower for the separation, and as a consequence, you see in both cases, you see the PT spectrum having like a little dip. Because you have one region of phase space where you have a K factor of 2 and a region of phase space where you don't have a K factor. And that kind of gives you a smeared out step. Okay. I will upload the slides. There's more stuff on it. I will try to upload it today, actually. If you're interested, look at it. Ask me questions tomorrow or over beer. And tomorrow we do this here, yeah? Okay, thank you. Ah, sorry. Do you have questions now? I'm too hasty. Sorry.
You said that for the coherence you would take like the subtraction function.
Yep.
I mean, you have lots of freedom in defining them, even some, I mean, on where the cutoff more or less is. If, like, for example, if you take like the alpha parameterization of the dipoles, whatever. Yep. So, I mean, does that make a big difference then in your...
It makes a difference in where you apply the K factor. Yeah? It makes a difference where you apply the K factor. If you make this separation, if you follow it through, then you can't make a mistake.
I mean, it makes a difference on where like
Exactly. It makes a difference It makes a difference where the transition between k factor and OK factor happens.
But is this strongly visible?
Yes, okay. So, okay, sorry. So, the logic is the following. If you do angular or so this is a really vicious observable. It's the rapidity difference between Jeter and Higgs boson, and this is a region that the parton shower in Herwig doesn't fill. Okay, and what you see is the following. If you compare POEC with MC at NLO, you see a difference in how it's being filled depending on how hard the jet is. You see a dip. And that is completely driven by k factor or not k factor for the parton shower to fill this or not. And can become really, really big. So if you run the parton shower alone, you never fill it. And this extra addition of this finite term saves it a bit, but you miss a factor of 2. Okay? This is for an angular ordered shower. We did a dipole shower based on Catani-Seymour subtraction and played with the alpha. And we get exactly the same dip. So it's completely driven. So you get these structures because, and this is by far the worst observable you can construct. You see the difference between a k factor factor 2 or not.
How do you choose, or which one is then the best one?
The best one there is to say, well, actually, if we look for another jet, we maybe use a matrix element for another jet on top at next to leading order. But then we would not do matching, but we would start doing a combination of matching and multi-jet merging, which I didn't have time to discuss. But you could do this by, instead of doing only Higgs alone at next to leading order, you could do Higgs plus jet plus Higgs plus 2 jets all at next to leading order. Use pseudo-conform factors to make everything nice and exclusive and add them up. And then all these dips vanish. The problem here is ultimately, you have an observable that depends on the first emission, and you look for first emission whether, to some degree, whether you do an estimate of a higher order correction on top of it or not. And if this estimate of the higher order correction is big, you see a big effect. It doesn't mean that the effect is necessarily that big, because it's an estimator only of a higher order that I took from an order from a different process. Yeah? Okay. More? Yes? No? Looks like lunchtime, huh? Okay.